I'm Dr Natalie Pridmore. I'm one of our crystallographers here in our crystallography lab. So this is our crystallography lab where we use X-ray diffraction to analyse the structures of molecules and materials. You may not have come across crystallography before, so just a quick explanation. It works similarly to a light microscope, except the distance between atoms is around 1 or 2 angstrom, and light has a wavelength of 400 to 700 nanometers. There's 10 angstrom in 1 nanometer, so we can't use light to see individual atoms. However, we can use X-rays because they're on a similar scale to the distance between our atoms. So if I fire my X-rays at my little methanol molecule, they'll be diffracted by the electrons in the atom in a similar way that light is reflected off an object. Therefore, we can work out the structure by looking at the diffraction patterns, because depending on which elements we have and their arrangement in the molecule, that will determine the diffraction pattern that we get. However, I can't look at just one molecule on its own because I won't get a strong enough signal. So to amplify the signal, we need to form what's known as a crystal structure. So you may have seen sodium chloride lattice before. So this is a 3D ordered array of our atoms, and while you get this for quite simple structures, calcium carbonate getting a bit more complex, we can also get a crystal structure for more complicated molecules. In order to form our crystals, we do this in a similar way that you may have done in an experiment where you have a blue solution of copper sulfate and you evaporate off the water in order to get big, bright blue crystals. So we can use similar methods, but we've got more solvents to choose from rather than just water, and evaporation isn't the only method that we can use. Depending on which crystallization conditions you use, you can actually get different crystal structures for the same material. And these can have different properties. For example, if you've ever had chocolate that's melted and re-solidified, you'll know that it never tastes the same. So even though it's the same material, its properties have changed because the crystal structure of the cocoa butter has now changed. If you also use different methods for crystallization, such as one of our research groups is using electromagnets as a way of accessing crystal structures that are otherwise very difficult to synthesize. So they're looking particularly at small pharmaceutical molecules. So if you've ever had paracetamol, particularly quite cheap paracetamol, you'll know you do your best not to taste it because it doesn't taste particularly nice. This is because they have to add binding agents to the paracetamol in order to make it pack into a tablet. However, if you can actually get paracetamol to synthesize in a different crystal structure, it's very easy to pack into a tablet and wouldn't require these binding agents. We can get many different shape sizes and colours of our crystals depending on both the molecule and how it packs in the crystal structure. However, what's not clear from the images is exactly how small our crystals actually are. This is our sample stage for our single crystal diffractometers. So the bottom part is a magnet that connects it to the instrument. Then we have a thin piece of glass which is amorphous, so it's not crystalline, it's not going to interfere with our diffraction. And on the very tip we have our little crystal that's about 0.2 millimeters in dimensions, although as we've seen we get different shaped crystals, so not every dimension is always 0.2 millimeters. And although this seems very small, it is small. It is a fifth of the smallest measurement on a ruler, but that's actually hundreds of thousands of molecules having to line up nice and neatly to give us that size crystal. This is one of our X-ray diffractometers. So we can see our crystal sat on the sample stage in the middle on what's known as a goniometer, and this moves around between measurements to allow us to collect diffraction data from all orientations of the crystal, which are then needed to help us work out the structure at the end. We then have our X-ray source, so when we're taking a measurement, our X-rays are fired along here, which focuses our X-rays onto our crystal. These are then picked up by the detector, and this then sends that information to the computer that we use to analyse the structure. We also have a video microscope that allows us to make sure the crystal's in the right position at the start, and we can see this on the screen here. And finally, what looks a bit like smoke is because we're cooling the crystal using liquid nitrogen to a temperature of 100 Kelvin, which is minus 173 degrees Celsius. The reason we're cooling to 100 Kelvin is because this limits the atomic motion and therefore gives us a clearer diffraction signal. However, we can take measurements at different temperatures, and this can be particularly useful if you have a material that can change structure due to temperature. So we've already mentioned that some materials can give different crystal structures under different crystallization conditions, but some materials will also change structure due to changes in light, temperature or pressure in the crystalline state. So, for example, some of our researchers are looking at materials that change colour due to changes in temperature, and this would allow them to have applications in things such as molecular switches and potentially sensors. So it's really useful to be able to analyse the change in the structure by looking at what structure we get at different temperatures and what's actually occurring when it changes colour. So here is an example of some of the diffraction patterns that we get from our measurements. So the size, the intensity and the position of these spots give us information about the structure. This would be the point with a normal microscope where we use lenses to refocus the image so that we can see and understand that by eye. However, we don't have lenses that work with X-rays, so we use some mathematical calculations that enable us to initially turn this information into an electron density map, and from there we can eventually get through to our structure. So this is the structure of a sucrose sugar molecule. So we can see it in 3D, we can see the bond lengths and bond angles. We can also see the hydrogen bonding interactions within the molecule. And because we're looking at the crystal structure rather than one individual molecule, we can also see how it interacts with other molecules within the structure. So this can give us a lot of very useful information. Another important thing is that we can even distinguish between chiral molecules. So these are molecules that are mirror images, such as your hands, so they're not superimposable, although they look very similar. So this carbon is chiral, so the two are not superimposable on each other. The hydrogens are in different directions when the rest of the molecule is the same way around. And for this particular molecule, one of these will smell like spearmint and the other smells like caraway, which is a kind of spice, because even though they're very similar, they have different properties. So these specifically interact differently with the receptors in your nose, and so you read them as different smells. So it's very important that we know the differences in our molecules, even down to the different chiralities, and this technique can allow us to actually look at that as well. We can also look at powders in thin films. So this is our powder diffractometer. So again, we have our X-ray source, and this time our X-rays are being fired at a much larger sample stage. And then we have our detector here. In this case, we also have a robot which allows us to set up multiple samples that can then be run consecutively. So, as mentioned, this instrument allows us to analyse thin films, potentially, say, a film that you've made as part of a solar fuel device, and you want to check that you've made the structure that you were intending to make, because that's the one that's going to have the correct properties for your application. So this is a quick non-destructive technique that allows you to check that structure against known structures for those materials and confirm if you've made the one that you wanted to make. So our robot is going to load our sample for us. And this works in a similar way to other spectroscopic techniques, such as infrared and UV-vis spectroscopy. However, in those cases, you keep your sample still and you change the wavelength and look at, in the case of UV-vis, you look at the change in absorption as wavelength changes. With this instrument, we have just one wavelength of the X-rays coming in, so instead we move the sample, as you can see, and the detector to allow us to collect data from different angles over the time of the measurement, and our sample stage is spinning to ensure that we're getting an average over the whole sample. What we end up with is something that looks like this. So we have angle along the bottom and intensity up the side. So anywhere where we see diffraction, we get a peak. And this is a bit like a fingerprint for our molecules. So this can be very useful for ensuring that you've made the structure that you had believed you'd made in the synthetic labs. So one important thing to note is that with all these instruments, we're looking at the materials in the solid state, and a lot of the time the researchers will be intending to use their material potentially in solution, particularly if they're making a new catalyst or a new potential pharmaceutical molecule. Therefore, it's still really important to carry out the other analytical techniques as well and ensure that how it behaves in the solid state is the same as how it behaves in solution, which is not always the case. That depends on the instrument, so you're looking somewhere between about 300 and 500,000 pounds. These instruments can last roughly 10 years. Often they can last longer than that, but generally the manufacturers will suggest 10 years. That very much depends on the instrument, so that's a bit different for the powder instrument to the single crystal instruments. The most likely bits to break any of the electronics can be so because we're using X-rays and they have a lot of health risks. There's a lot of safety features that ensure that you're not exposed to the X-rays, and all those safety features are controlled by microswitches that, when engaged, will let the instrument know that it's safe to run. So if any of those break, we check the instruments monthly to make sure that we're not seeing any more than background radiation that we'd expect. Yeah, normally both. So we get a mixture. So anybody that's producing structures can get trained to use the relevant instruments. For the undergrads, if that's not the main focus of their project, sometimes they don't want to learn to run all the samples themselves if they're only going to do one over that whole project, but they can still come down and see how it works. But if it's going to be quite a big part of their project, then they can get trained the same as the PhD research students as well. For the powder, it's an hour for the instrument training, and there's also, before that, there's radiation safety training. For the single crystal, it's a few hours, so normally about half a day for the initial training, but then you'll be supervised the first few times you use it until proven competent enough to then use it on your own. So it's a little bit more complex for the single crystal instruments. They used to be done by hand, these calculations. So when crystallography first started, rather than the complex detectors we have now that send all the information to the computer, you would use a photographic plate to measure your diffraction onto, and then take that and by hand work out the positions, and then use that to calculate your electron density map and therefore your structure from that. So these calculations can be done in person. So yes, the calculator could be employed, but it takes a lot longer to do it that way. So structures used to take months, if not years, to potentially solve, whereas now we can collect the full data set in a few hours and fully process and complete the structure maybe in about half an hour after that. Yeah, just a normal desktop computer. So particular software is needed in order to be able to process the data and to visualize the structure, but with that can be run on any computer. You sometimes get structures that were not what they were expecting, or sometimes your crystal structure might actually be a mixture of more than one structure, and you have to then work out and separate those. I particularly like a structure that we got that the structure itself wasn't weird, but due to hydrogen bonding, it had formed into a kind of hexagon shape, and the crystals themselves were little hexagons as well. So the shape of the crystal was from the intermolecular hydrogen bondings that you got, and yeah, I quite enjoyed that one.